Dr. T.V. Geeta, Professor, Department of Computer Science, College of Engineering, Guindy, Anna University. Her special interest, Artificial Intelligence and Natural Language. She has published more than 143 articles in national and international journals. She has guided around 7 PhD students. She has got Young Scientist Award from Government of Tamil Nadu in the year 2000, Chief Minister's Special Mention Award in the year 2002, and Woman of Excellence by Rotary Club in the year 2003.
Welcome to the UGC lecture series. In this lecture, we are going to talk about normal forms. We are going to talk about first, second, third and the Boyce Codd normal forms. In this lecture, we are trying to understand the normalization which is based on primary keys and on relations. We are going to understand the first, as I already told you, the first, second and third normal forms, and we are going to understand what is meant by Boyce Codd normal form. So, there are a number of normal forms available, of which the normal forms based on primary keys are first going to be discussed. So, what is first normalization? In any situation, normalization is bringing all the data that is available to you in a normalized manner such that you can compare. Okay, that is the meaning of normalization. Here normalization of data is a process during which in relation to databases, which unsatisfactory relation schemas in the design are decomposed. How are they decomposed? By breaking up the attributes into smaller relation schemas and which possess desirable properties. So, what we are essentially doing during the normalization process is trying to find out whether a design schema that you have satisfies some desirable property. If it does not satisfy the desirable property, we are trying to split the attributes such that the property is satisfied. As we already saw in previous lecture, we found that there are certain problems when we do insertion, deletion and updation if you do not have proper design. So, one of the aims and objectives of the normalization process is to ensure that such type of update anomalies does not occur. Normal forms, however, do not guarantee a good database design, because finally the design and how you define the functional dependency depends on the design. You cannot, just because it has all those properties does not mean that it is a good database design, but it takes you towards a good database design. Normal forms are basically, they are based on primary keys, and when we are doing the normalization process, two properties must be preserved. One is lossless join and one is dependency preservation. That is, when you join two tables, you should not, when you are joining, you should not lose data. That is what is called as lossless join. We will go a little more in detail about this later. And then one is dependency. After all, the attributes are dependent on each other. You cannot remove the dependency, because as an automatic procedure, whatever the designer has decided is the dependency, you cannot remove that. Now, we said that it is dependent on prime attribute, we call prime keys. So, primary keys, any attribute associated with the primary key is called the primary attribute, and which is not belonging to the primary key is called a non-prime attribute. So, there are two types of normalization. One is normalization based on primary keys and the other is the normalization based on relations. So, the first normal form is based on primary keys, and the second, third and the Boyce Codd normal forms are based on keys and the functional dependencies of a relation schema. While we are not going to discuss this here, the fourth normal form is based on keys and multi-value dependencies. We will go into what is multi-value dependencies later. And the fifth normal form is based on keys as well as join dependencies. Join dependencies are nothing but additional properties may be needed to ensure a good relational design, like lossless join and dependency preservation, that is also needed. So, now we have looked at, there are 3 or 4 groups of normal forms. First normal form is decided only by the keys. The second normal form is decided by the keys and the relation schema, the FTs of the functional dependencies of the relation schema, which functional dependency you know what that is. The fourth normal form is dependent on the key and multi-valued attributes or dependencies, and fifth normal form is dependent on the keys and the join dependencies. Join dependencies, what dependencies come into the picture when you are joining tables. So, what are the practical uses of normal forms is the next question that we want to ask. So, normalization is carried out in practice so that the resulting designs are of high quality and meet the desirable properties. But finally, the initial design has to be good, otherwise it is not So, there is no guarantee that it will be a good design, but if you follow this, then the quality will be better and it will have desirable properties. the practical utility of these normal forms become questionable when the constraint on which they are based are hard to understand or to detect. So, the database designer need not normalize to the highest possible normal form. Normally, they go up to 3 third normal form or Boyce-Codd normal form, very rarely up to 4th normal form. So, it does not go up to 5th normal form. And denormalization, the process of storing the join of higher normal form relation as a base relation, which is in normal lower normal form. This is also sometimes done. So, please note, when you talk about normal form, anything that is in second normal form is also in first normal form, anything that is in third normal form is in second and first, and anything in fourth is in third, so on so on. So, that is a basic property of normal forms. Now, let us look at what we mean by normalization of relations. Now, the process of decomposing unsatisfactory bad relations by breaking up the attribute into smaller relation is called relation normalization. Normal form condition using keys and FDs of a relation to certify where a relation schema is in a particular normal form. So, normal form of a relation is the highest normal form condition that it meets and hence indicates the degree to which it has been normalized. So, the more higher the normal form, the better the degree of normalization. So, again as we already told you, the relation, we are not talking about the keys, that is the first normal form, we will come back to first normal form later, but here we are going to talk about only the relations, the normal form associated with keys and relations. So, second, third and Boyce-Codd normal form are based on keys and the functional dependency of a relation schema. Fourth normal form already as we have told based on keys and multi-value dependencies, and fifth normal form on based on keys and joint dependencies called JDs. Before we go further, let us define some terms that are needed for understanding normalization. So, let us first define what is meant by a super key. A super key of a relation schema R equal to A1, A2 to AN is a set of attributes S, which is a subset of R, that is out of this A1 to AN you take a subset, small subset, and that subset will have the property that any tuples associated with that subset. So, T1 and T2 are 2 tuples, any 2 tuples you take, and you take only those attributes, they should be the will have the same values, those two. Then that set of attributes is called the super key. A key K is a super key with the additional property that removal of any attribute from K will cause K not to be a super key anymore. This is the definition of key that we are giving here. So, you have super key and you have key. Super key is a set of attributes that will have the same values across tuples, okay, that is the super key. Now, out of that super key, if you remove any attribute, okay, it will cause K not to be a super key. Then if you do not have any such attribute, then K is called a key. Now, if a relation schema has more than one key, each of the keys is called a candidate key. One of the candidate keys is arbitrarily designated to be the primary key and the others are called secondary keys. This is just definition which we have already seen in previous lectures, but just a repetition to summarizing this. A prime attribute must be a member of some candidate key. So, not all candidates key are primary key, it depends on the designer. A non-prime attribute is not a prime attribute, that is it is not a member of any candidate key. So, now what are the terms we have seen? We have seen what are the terms super key, we have seen the term key, we have seen the term candidate key, and then after candidate key one is chosen, that is the primary key, the other candidate keys are the secondary key, and we have seen what is a prime attribute. Any attribute that belongs to the candidate key is called a prime attribute, which does not belong to the candidate key is called a non-prime attribute. Now, let us look at the first normal form. Now, let us look at up to now we have looked at normal forms. Now, let us take the first normal form. Now, what are the properties of the first normal form? The first normal form disallows composite attributes, multi-valued attributes and nested relation. What is nested relation? Attributes whose values for an individual tuple are non-atomic. So, this is considered to be a part of the definition of the relation. So, here we are talking about some attribute features or key features, and first normal form disallows all these three. What is the definition? So, first thing he said is composite. So, we want it to be atomic. So, a domain is atomic if its elements are considered to be indivisible units. Example of non-atomic domains are set valued attributes and composite attributes. Identifiers like CS101 that can be broken up into parts, that is CS for the department and 101 for the subject number. These are called also as non-atomic. So, it is not that they have to be separated by blanks and all that, it depends on what the meaning says. If your database is going to consider these two as separate, then it becomes a non-atomic domain. A relational schema R is in first normal form if the domains of all attributes of R are atomic. So, as I already told you, why non-atomic values complicate storage, encourage redundancy, and interpretation of non-atomic values has to be built into the applications programs. So, these are the reasons why the first normal form tells you to avoid these things. We want only atomic values. So, atomicity is not an intrinsic property of the elements of the domain, you have to make it atomic. So, atomicity is the property of how the elements of the domain are used. Example, strings containing a possible delimiter, here space, cities, Melbourne city, this is non-atomic because this space which separates the list Melbourne and Sydney. Now, this surname Fortescue Smith is actually an atomic, though it has a blank here, because this is never going to be used separately, this is going to be used as an entire string, and so this surname is atomic. So, it is not decided by the blank space. Strings encoding two separate fields, this we have already discussed. Student ID is equal to CS 1234, though this comes together without a blank. If the first two characters are extracted to find the department and the domain of the student identifier, now here that is not, then it is not atomic. So, leads to encoding of information application program rather than in the database. So, let us look at this example. Now, this example you have department, you have department name, department number, department manager SSN and department locations, and in department you have, now here the problem is we have this schema has been populated with instances. So, you have research department number is 5, department manager SSN is something, but the locations are in 3 places. So, this is a multi-valued attribute. So, in order to convert this into normal form, you have to necessarily repeat these research 3 times and have it as separate tuple by breaking up this non-multi-valued attribute. This is in first normal form, while this is not in first normal form. That is an example of got a non-atomic attribute or a multi-valued attribute converted, a set based multi-valued attribute converted into a first normal form. The next is the nested relation. Now, if you look here, you have SSN, e-name, and then you have projects which has 2 components, P number and hours. So, here you have the employee project, okay. Here you have SSN, e-name, and then project number, and then hours, project number 2 and hours 2. Now, if you have it like this, this is not a first normal form. So, it is better to divide this into SSN e-name and then have SSN P number and hours, so that it becomes into first normal form. So, here we are talking about nested relations, where we have to again spread it out, so that it becomes first normal form. Now, we will continue after the break. Welcome back after the break. Now, before the break we have looked at the first normal form, where we tried to expand the multi-valued attributes and the nested attributes non-atomic. Now, let us go to the second normal form. Please remember, the second normal form is also in first normal form. Here the second normal form uses the concepts of functional dependency and primary key. Now, let us look at some definition again. Prime attribute, you remember, is an attribute that is a member of the primary key K, and full functional dependency y equal to z, where removal of any attribute from y means that the functional dependency does not hold anymore. So, these are the 2 definitions we are going to use. For example, SSN P number equal to hours is a full FD, since if you remove the SSN or the project number, the hours will not hold. Okay, if you remove SSN hours or P number hours do not hold. So, this is a full functional dependency, while SSN P number E name is not a full dependency, it is only a partial dependency, because if you remove this SSN going to E name still holds. Remember, this is an employee name. So, this is not a, this functional dependency is not a full functional dependency, while this is a full functional dependency. A relational schema R is in second normal form if every non-prime attribute A in R is fully functionally dependent on the primary key. R can be decomposed into 2 normal form relations via the process of second normal form normalization. Now, let us look at this example. You have an employee project, and these are the functional dependencies. SSN P number determines the hours, that is FD1, then SSN determines E name, that is the second functional dependency, then P number determines P name and P location, that is the third functional dependency. Here we can split this into SSN P number hours as the first table, SSN E name as the second table, and P number, P name and P location at the third table, instead of having it as a single table because of the functional dependency properties. That is the second normal form. Now let us go to third normal form. This is the definition is, remember the transitive functional dependency, x goes to z can be derived from x goes to y and y goes to z, we have already seen this. Now suppose you have SSN determines the department manager SSN, it is a transitive FFT because SSN determines D number and D number determines the manager. So SSN E name is non-transitive since there is no set of attributes x where SSN equal to x and x equal to E name. A relation schema is in third normal form, as I already told you, if it is in first and second, and non-prime attribute A in R is transitively dependent on the primary key. R can be decomposed into 3NF relation via the process of 3NF normalizations. For example, consider employee SSN, employee number and salary. SSN functionally determines employee number and which in turn determines salary. So, employee number is a candidate key. Relation is in third normal form if whenever x functionally dependent on functionally determines A holds, either x is a super key or A is a prime attribute. Informally, everything depends on the key or is in the key. Despite the thorny technical definition that lead up to it, 3NF is intuitive and not hard to achieve. It is better to aim for it in all designs unless you have strong reasons otherwise. So, let us look at this example again. You have the employee department. Now, the 3NF normalization will split this into two, where you have SSN is the primary key, SSN E name, SSN determines E name, birth date, address and D number, and the D number is split here because otherwise what will happen is SSN determines the D number, but all these other attributes do not determine the D number. So, this way we have split the two, this is the 3NF, this is intuitive enough though technically we talk about it. So, the algorithm is you get the minimal cover of FDs, the cover we have discussed in the previous lecture. Find a lossless joint decomposition of R, add additional relations to the decomposition to cover any missing FDs of the cover. The result will be lossless, we are not going to prove that, and will be dependency performing, but may not be in Boyce-Codd normal form. So, just to informally revise, first normal form all attributes depend on the key, second normal form all attributes depend on the whole key, that is much more of a constraint than this. Third normal form all attributes depend on nothing but the key. So, this is the actual definition of the informal definition of first, second and third normal forms. Now, above definition consider the primary key only. The following more general definition take into account relations with multiple candidate key. We assume that there is only one primary key. So, our relation schema R is in second normal form if every non-prime attribute A is fully functionally dependent on every key of R. So, the super key we have already seen the definition. So, X is a super key of R or A is a prime attribute of R. So, this is what we talk about in third normal form. Boyce-Codd normal form disallows condition B. So, this is not allowed, that is a more stringent definition. So, there is only a slight variation between third normal form and Boyce-Codd normal form. So, relation schema R is in Boyce-Codd normal form if whenever this relation holds good, x goes to A holds in R, then x is a super key. Each normal form is strictly stronger than the previous one, this I have already discussed with you. Second normal form is in first, third is in second and BSNF. So, the order is first, second, third and BCNF. So, there can be relation that exists in third normal form, but not in Boyce-Codd. The goal is to have each relation is either in BSNF or Boyce-Codd normal form or in third normal form. So, look at this is the third normal form. Here you have functional dependency property determines county name, lot and area. The county name and the lot determines the area and the area determines the county name. So, if you do BSNF normalization, you will get property ID, area, lot, and you will have area and county name. So, BSNF normalization of lots with functional dependency FT2 being lost in the decomposition. This is a schematic of FDs, it is in 3NF but not in BCNF. You achieve the BCNF by decomposition. So, two FDs exist in the relation teach, we are taking another example. So, FD1 is student course instructor and FD2 is instructor course. Now, student course is a candidate key for this relation and the dependency shown follow the pattern. So, this relation is in 3NF, but it is not in BCNF. A relation not in BCNF should be decomposed so as to meet this property. So, instead of having it like this, we can split it into this two: instructor course is 1 and instructor student is 1. So, this can be done so that it becomes equal to Boyce Codd normal form. If you look here, look at this, this is a relation which you have student, course and instructor. Now, student course determines the teacher, student course determines the teacher, student course determines the teacher, but you also have the instructor determining the course, instructor determining the course. So, this relation is in third normal form, but is not in Boyce Codd normal form. Now, if you want it, this is an example of a relation in Boyce Codd normal form. So, you have title, year, length, film type, studio name and star name. Title, year, star name is a candidate key and title, year, length, film type, studio name, that is the other functional dependency. This violates the BCNF condition because the title and year do not determine the sixth attribute star name. That is the problem with this thing. So, what you do? We solve this by splitting it, the schema with all the attributes of the FD, title, year, length, film type and studio name, schema with all the attributes of MeWe except the 3 that appear on the right of the FD. So, look here, these 3 alone are put separately and the others are all put together. The definition of BCNF is a relation schema R is in BCNF if for every FD x equal to y associated with the relation either y is contained in x, that is the FD is trivial, or this x is a super key of R. So, for example, you have a person 1 relation with SSN name and address and the only FD is SSN which indicates name and address, then SSN is a key and person 1 is in BCNF because SSN determines both the name and the address. Now, suppose you have SSN name address hobby. Now, SSN name address does not satisfy requirements of BCNF since the key is SSN hobby, SSN and hobby. So, has account number, client ID, office ID. Yeah, account number, office ID does not satisfy BSNF since keys are client ID and office ID and account number, client ID, not account number. So, all this together tells us what are BCNF. A simple condition for removing anomalies from relation. So, BCNF is a very important normal form, that is what. So, you have whenever there is a non-trivial FD A1 A2 going to be for R and A1 A2 AN is a super key for R. In English, whenever a set of attributes of R is determined another attribute, it should determine all attributes of R. Just to continue with the discussion, find the dependency that violates the BSNF condition. So, you have A's here and B's here, choose B1, B2 to Bm to be as large as possible. So, continue until there are no BCNF violations left. See here, name, SSN, age, eye color, phone number. The functional dependency is SSN determines name, age and eye color. Okay. Now, if you want it to be in BSNF, you have to split these two as SSN name, average, eye color, which you have taken from this FD and this SSN which is on the left hand side and all attributes that are not covered in this, that is the phone number. So, now you have split these two. So, in essence what we are doing is, so if you had also an attribute draft worthy and the FD age determines draft worthy, then that will also come as an other relation. So, a relation schema R is in 3NF if it is in 2NF, this we have already seen. This is again, this is just to make you understand this 3NF and BCNF in a better way because, so here look at this, we are also taking the tuples here. Consider this R A B C D and A to D holds and D to A holds, B C D is also a key. Therefore, R is in 3NF. However, A and D may still occur redundantly, therefore, this is not in BCNF. If you look here, SSN name address is 1 and SSN hobby is 1. So, this SSN name address has to be put in 1 and all this along with SSN has to be put here. Now, again this we are revisiting this account number, client ID and office ID. Account number, office ID is the functional dependency. So, what you will have to do is you have to take account number, client ID and put it as another relation. So, this results in some redundancy. So, for example, suppose you have SSN name address hobby. So, these two together is SSN name address which is actually redundant and SSN hobby is not redundant. So, this is a redundancy problem. If A is a super key, there cannot be 2 rows with the same value of A. So, BCNF sort of eliminates redundancy also. So, this is one important property of BCNF, because when you put this separately as say SSN name address, you will have only one value, one tuple. So, this is the example we have already seen. Another example, let us take. Now, supplier part is supplier number, supplier name, part and quantity, and you have two candidate keys, supplier number, part number, and supplier name, part number. Supplier number, part number equal to quantity, supplier number, part number equal to supplier name, supplier part number is equal to quantity and supplier number. Now, if you look at this, you have to divide this into 2, because supplier and part number gives quantity. So, you have to have supplier part number, supplier name as another relation. So, this is again another example showing the hours and the this thing. Now, if you look at this, is this in R goes to W. So, is the relation BCNF? No, the second FD causes a violation, W value is repeatedly associated with the R values. Up to this point, we have explained what it means by basic normalization and explain the examples of first, second, third and Boyce-Codd normal form. We have taken extra care to explain the difference between third normal form and Boyce-Codd normal form, because it is better to have a design in the most designers try to achieve the Boyce-Codd normal form. One of the advantages we already saw of having Boyce-Codd normal form is lot of redundancies can be reduced. I have given you an example. Consider the following relations for an order processing application at this, and try to, this is a typical process and exercise that you will have to do, where you will try to convert this into the normal forms. Now, assume that each item has a different discount, the total prices, all this is given to you, and you have to convert, find out what is the key. This is like a design application. You have to find the resulting relation schema, what is the key, the FD's resulting relation, show the FD's in this resulting relation, is it in 2NF, is it in 3NF, why and why not. Another example for the same type of problem, again we are asking you to find out why, what is a key, whether it is in 3NF and BCNF, and give proper reasons for this. You have to also find out whether the decomposition will be lossless and show why is it lossless. Then I have given you some theoretical problems to explain what are these terms, and explain this and explain why BCNF is stronger than 3NF, and if you take consider any unnormalized relation and convert it into 1F, first normal form, second normal form and third normal form. So, thank you very much.